The main portion of NeurIPS 2022 just wrapped up about a week ago, and considering that NeurIPS is one of the biggest conferences in the space where some really awesome research is published, I thought it would be fun to go over the best of NeurIPS. Now, these are not my best of NeurIPS. These are the papers that got outstanding paper awards from the actual conference itself. There are quite a bit of them. I think we have like 10 plus, I think a little over 10. Plus we have 2 datasets / benchmark papers. And the plan is going to be to essentially go over these at a high level. I'm not going to go in depth into every single paper because that would take an eternity. But I do want to sort of touch on each of these because, I mean, they got outstanding paper awards for a reason. Lots of them are pretty cool. We are going to dive into the first one very shortly. Now, just a heads up, what I did to prepare myself for this is I read over all of these summaries. I went to each paper. I read the abstracts. I read the introductions. I skimmed over most of the papers and read a bit more of some of them, but I have not read most of these in full. I'm probably going to get a thing wrong here or there, but hopefully most of this should be right. So the last thing I'll tell you about before we get into the first paper is about ClearML, the sponsor of this video. ClearML offers an end-to-end platform for ML ops where you can do everything from tracking experiments to automating an entire machine learning pipeline through to deployment. Here's the code for one of my current projects, and with just an extra several lines of code, I can integrate it with ClearML. And with that, we can now pull up a dashboard and see the progress of my experiment as it runs. Here, I'm just logging the loss because I wanted to get this done in a few seconds, but there is a lot more you can do with this. But really, this is just the tip of the iceberg. You can also create entire pipelines that pull in different versions of your datasets, run hyperparameter sweeps, automatically set up new environments, and because of that last point, ClearML has no problem with scaling. As I run many experiments in my own research, I personally love some of the features that help me with that. For example, I love how ClearML not only tracks code version, but also uncommitted Git changes, which is very nice. And also how through the dashboard, I can inject configs into my experiments, which means I don't have to constantly be modifying my code to run a bunch of new experiments. If that sounds like something you're interested in, you can try out their product for free by following the link in the description below. And now let's finally get into this first paper. The first paper we're taking a look at that got this award is out of distribution detection learnable? If you aren't familiar what out of distribution data is, it's essentially data where, when we're training a model, we typically expect data to fall into a certain pattern or a certain distribution specifically, right? So if we are training on data from Pac-Man, maybe we only train on the first level, well then data from the second level of Pac-Man would be out of distribution data. Specifically, this paper deals with, oh my gosh, my voice, is how do we detect, oh, that's not what I wanted. How do we detect out of distribution data? Working with out of distribution data is, I think, a notoriously hard problem in ML, and to work at this issue, what they use, and this is the most hilarious technical term ever, is probably approximately correct learning theory. Now, this is a technical term. Pack theory is, I'm pretty sure it's pretty old. I remember learning about it in my beginner ML class, and God, I hated this stuff. It's theory, though, essentially about how you can figure out if something is learnable or not, and do that in a rigorous and mathematical way. And that is right, this paper is a theory paper. If you scroll down, you can see that's what most of this paper is. Though I will say, I did actually read a decent portion of this paper, and for a theory paper especially, it's very well written. I could actually understand what was going on in most of this, even though I forgot almost everything about PAC. But, I guess maybe that's part of the reason it got an outstanding paper award. In terms of what they actually deliver on that front, what they do is they get some conditions. So here they say it right here, they have some necessary conditions. And once these conditions are met, they say that learnability of OOD detection can be done, or whether it is learnable. And then I didn't quite get to this part in the paper, but they do also say that they give several necessary sufficient conditions such that they can characterize the learnability. And I think this is cool in practical scenarios. Generally, when I see people working with PAC, it's usually pretty out there. These things usually aren't applied. I'm not sure if I would call this paper applied or not, but if they do actually give some practical scenarios, that's awesome. If you can do out of distribution detection, that really touches on so many different problems on ML that the impact for something like this could be very big. On to the next paper. Next, we have photorealistic text-to-image diffusion models with deep language understanding. And this paper is probably more commonly known as Imagen or Imagen. I imagine it's Imagen, right? That makes more sense. And this paper is from Google. This actually came out a bit ago, several months ago, I think. And it was funny because it came out not too long after DALL-E 2. Now, hopefully I don't need to explain what DALL-E 2 is at this point, but what was crazy was how soon after this came out and the fact that Imagen actually, I think, had better metrics. It was doing a little bit better. I'm not going to sit here and explain what this paper does because most of these text to image diffusion models work similar ways. Maybe some of the details are different, but, I'll just let you look at these lovely pictures, lovely corgi in a sushi house. That's probably my favorite. And just a quick interjection, if you're finding this interesting, consider subscribing to the channel. I cover a whole lot of big papers to keep you up to date, and also some smaller ideas to introduce you to, smaller, more niche ideas. And now that you've gotten your fill of text to image generation for the day, we can move on to the next paper. Now, surprise, surprise, or maybe no surprise at all, the next model also happens to be about diffusion models, or diffusion-based generative models, as they say, same thing. And the idea here, though, is not giving a new text to image model, but rather looking, and I really like this, they take, because now we have so many of these models, as I mentioned before, they all have the same core ideas using the sort of diffusion models, but within those diffusion models, there's different types of samplers, different ways they apply noise, different ways of doing all these things. And this paper takes a look at those from a really, and I quote, a practical standpoint, looking at what they say are the tangible objects and the sorts of algorithms that are appearing during training and sampling phases of these, which is nice because there are so many of these, and they essentially give a better framework for looking at this that is more modular and allows you to probably better make design choices when you're trying to design a good diffusion model. They do give a few concrete examples of this. So one is how to better do the sampling process. And here they say they identify the best performing time discretization for sampling. Sampling, I believe what they mean by that is how, when they're going from, doing these multiple steps you see here, how they actually do that. How do they decide what the steps are? Because typically, if you've used a diffusion model, it can take many, many steps to generate very good images. And what they actually mention is that they have in their work here been able to reduce this using a more solid method so that you actually don't need to use as many samples to generate high quality images. And another thing they do is they give some methods to help improve the training dynamic. And to do this, they use things like changing the distribution of noise levels. What is this non-leaking augmentation? I don't know exactly what that is, but I'm sure it's some sort of augmentation, as it says right there, is beneficial for diffusion models as well. So they're giving some essentially very practical ways that people can improve their diffusion models, which is great. So many people are using this right now. I could imagine lots of people would find this super useful. The next paper is ProcTHOR, large-scale embodied AI using procedural generation. This one is a great practical work that provides a new environment for doing these sorts of embodied AI experiments. You might have seen that I think there's been some, especially work from Google recently, doing this sort of thing where you can use language to instruct an agent to like pick up objects or move things around. You could do that somewhat in real life, but that's really hard and it can go much faster if you simulate it. Now there are robotic simulations like MineDOJO and stuff, and there are some things where you can move around in a world, but I don't think there's probably been anything on this scale yet. As you can see right here, the idea here is that everything is customizable. You can randomize everything, which, I guess the idea is that that should hopefully help with generation and evaluating in different environments. And I'm not even going to show you the paper anymore. I'm just going to show you they have a website here. As you can see, this looks really great. They have, I believe, 108 object types, different types of objects that you can place in these rooms. Then there are 1,633 different instances of specific objects. And then you can also do things like randomizing the textures, the lighting, all that sort of stuff. As you can see right here, we're getting some very different rooms. This is just great. I mean, who doesn't like to see these new things? There are two things. One is that this paper has done the most incredible thing ever. It got a paper published with a emoji in the title. Has this happened in NeurIPS before? I'm very curious. Someone let me know if you knew of anything like this. The other thing that I thought was funny was actually looking at the reviews. Even though this got an outstanding paper award, there was a reviewer that gave this, yes, a 4, which is a borderline reject. I mean, they did not think this was a great paper, or at least they didn't think it was good enough to get accepted. And their main reasons for that was that they didn't do enough. I don't know how this isn't enough. And this isn't the only paper that got, 1 or 2 bad reviews, which I thought was funny. Even some of the papers that end up getting outstanding paper awards still have some quite negative reviews. The next paper we have is using natural language and program abstractions to instill human inductive biases in machines. It's quite the mouthful, but it does actually explain quite well what's going on here. We are trying to, in this paper, instill our human biases into our AI agents. Now, why might we want to do this? Well, in the very first sentence here, they actually give us a good idea. It's that strong inductive biases give humans the ability to, key here, learn quickly, learn very quickly, or quickly learn to perform a variety of tasks. And how do they do that? Well, they use a set of auxiliary tasks. So if you actually scroll down, they have a nice little example here. So here is what the agent might be trying to do in the little grid. But then what they'll do for the auxiliary task is they'll also write this out in perhaps language, or maybe give it a target board or some representation that a human would use to describe what's going on here. And then they will essentially train on both of these at the same time. Not only does the agent have to get this path, but it also has to predict what the language would be. So it's trying to bias the agent in the way that humans would do these things. What the results showed was that yes, these agents do perform more quote unquote human-like, or they use more human biases. So that is good in the sense that it might help them learn faster, but we also have to remember that this can be a double-edged sword. Well, this might be good if we're doing a task humans are good at. We have to remember humans are not the best at everything. To give an example of this, we could look at something like AlphaGo, which was originally an area where computers were not performing super well, but more recently, computers are doing really well and outperforming humans significantly, and that's an area where human biases might not help so much, right? So this is a double-edged sword here, and that is what they found. While these agents do maybe pick up some of the good things that humans are doing, they also picked up some of the bad habits, which is not so great. But that was the goal of the paper. Can we get them to do these things that humans do? And I guess the answer there was yes, by using these sorts of auxiliary tasks. Next up, we have a neural corpus indexer for document retrieval. This is a paper where they're doing exactly that. They're doing document retrieval. So this would be like a search-based thing, where maybe you put in some query and you want to get the most similar document to that query. The way this typically works is there are usually two steps, as they note here. The first thing that typically happens is document retrieval. This is where the algorithm will go through and it will get a bunch of documents that might be similar to the query. And then the second thing that happens is those are ranked. So we'll rank those in order, maybe just grabbing the top one or maybe showing them in order of relevancy. Instead, what they do in this paper is they combine both of those two steps into one end-to-end neural-based architecture. Now, specifically in that architecture, this is one of their contributions, is that it's end-to-end differentiable, which means that you can actually differentiate back through the document index, which means if you find that a specific document, say document number 210 is the one that's most relevant, you can actually back propagate through that to the first part of the algorithm that chose that document. And that's what allows this whole process to be end-to-end instead of having to split it up into two steps like previous works have typically done. Now, through this model, they actually do seem to get state-of-the-art results. I'm always skeptical when I hear this because I haven't looked at these, but you know, that's what they claim, and it did get an outstanding paper award. So that's awesome. And they claim that the reason that their method can do this is typically the ranking phase of an algorithm. You know, all they can do is they can take the embeddings of two documents and they essentially have to compare them using something like cosine similarity, which is a pretty shallow metric. It can only find certain correlations. However, what they're doing here, because the full architecture end-to-end is a neural-based architecture, and they're actually passing two documents through a neural network together, they're able to use an attention layer that's able to potentially grab many more complex interactions between the two documents, the idea being that they might be able to identify more complicated similarities. The next paper we have is high dimensional limit theorems for SGD, which is stochastic gradient descent, effective dynamics, and critical scaling. Now, I spent a good bit of time going over this paper, reading and rereading, and what I took away from all of that was that I have no clue what the heck's going on. Unfortunately, sometimes, you know, I don't understand papers too. It happens. I can't be an expert in everything. And this paper is theory down to the bone. Really what I got out of this is that things get really wacky and complicated when you are doing SGD in high dimensions. I'm sure the paper is really neat. Unfortunately, I can't give you guys a good description, so we're just going to move on. Next, we have gradient descent, the ultimate optimizer. This one is also about gradient descent, but thank God I understood this one. This one was a much simpler. And this paper is simple, yet seemingly very nice. And it also comes with a library that you can actually use, which I love that. So what this paper does is the idea is quite simple. Oftentimes when we're doing machine learning, not oftentimes, pretty much all the time, we have hyperparameters, and you have to optimize those hyperparameters. You have to fine tune your models, which can be a pain. It can take time. So lots of methods, or a good bit of methods, have tried to address this. What this method does is, well, it does try to address this by essentially optimizing the hyperparameters with more optimizers. So you're stacking optimizers on top of optimizers, and you can keep stacking them as high as you want. So maybe you're using Atom to optimize your main neural network, and then to optimize Atom, so the different parameters for that, you could have SGD. And then if you want to optimize the SGD, you could have SGD optimizing that SGD. And you can keep stacking these up as many times as you want. I really wish they had a graphic for this. just stacking up optimizers because it's kind of funny. But that's really the whole idea in the paper. Here's sort of a diagram of roughly how it works. And what they found by doing this is that essentially the more optimizers they stack on top of each other, the less sensitive the results become to the initial conditions of those hyperparameters. Now, of course, I imagine there's a cost to do this. The cost associated with doing this sort of meta hypergradient tuning sort of thing can be pretty high. I haven't tried it out, so I don't know. But they do have a library, so do try it out if you're interested. I am certainly going to try this out in one of my next projects. This is what I was looking for. They have the Atom and then the RMS prop and the SG and the SG, and they're all optimizing the one below them. It's great. So if you want to try this library out, it is here for you to try. Now let's get to the next paper. And next is Riemann score-based generative modeling. And by score-based generative model, that's essentially a diffusion model, or what has popularly become known as a diffusion model. And here, what they're doing is they're really just extending the work of diffusion models. Typical diffusion models, the theory and all the equations, they work on a Euclidean space, as they note here. And the idea here is that they want to extend that to a Riemann manifold. And what that means is that they don't have to necessarily work on that Euclidean space. For example, an image, right? It's just a 2D grid of pixels. Well, if they extend that, there you have a good graphic down here that shows an example. For example, the surface of a sphere. And that could be useful when you're doing something like predicting maybe populations on a globe or wildfires. I have to scroll down a lot for this, but they do have a good graphic. Here it is. So here you can see that maybe you want a generative model that predicts where earthquakes are or something like that. Well, I guess you probably could have done that previously, even with a Euclidean diffusion model. The issue there is that I guess it might be warped, right? I guess it's kind of like when you try and put the globe into a 2D image and then predict things, and then you have to compress it again back to a globe. I would imagine there's probably some sorts of distortions and stuff. So perhaps that's what this method is avoiding. So I guess this method could be useful in cases like that. Next up, we have gradient estimation with discrete Stein operators. And what they take a look at in this paper is cases where we have a model that is outputting some discrete values. So they give two specific examples of this. One is reinforce. Reinforce is a reinforcement learning algorithm where you can use this for like discrete action spaces, right? So where your agent can take one of several actions, maybe up, right, left, and down. And then the other case they take a look at is that of the VAE, or the variational autoencoder, with a discrete latent space. And that is where you're trying to compress something down, maybe like an image, into a set of discrete vectors, and then reconstruct it. And by doing so, you're learning a sort of compressed discrete representation. What they point out in this paper is that when the distribution that you're learning is discrete, most common gradient estimators suffer from excessive variance. And that essentially means that they could end up being very difficult to train, and that is not ideal. So what they do in this paper is they introduce a new way of designing control variance, which is a technique used to reduce variance. And that technique uses what's called Stein operators. Overall, if you can reduce this variance, which they show they do successfully, well, that should help out learning. And while this might seem like a quite minor problem, well, learning discrete distribution is something that is touched on or used in many areas of machine learning. So you can imagine that having an impact on this problem could actually touch a lot of problems in machine learning. Next up is a paper I've actually covered before on this channel, and it is training compute optimal large language models. Now, this is a paper from DeepMind where they point out, obviously LLMs are getting very big. These large language models, they're called large language models for a reason, and they are costing a lot of money to train. Now, when you are working with these large models and you have a budget, you want things to be trained as efficiently as possible, right? Even if you can make a 50% or 20% improvement in training efficiency, that can save you potentially millions of dollars when you're getting into the big money people are pumping into these models. Now, previously, there was a paper that did this from OpenAI, and it examined if we train a bunch of models at different sizes, what are sort of the scaling laws? How should we train these? What parameters should we use? How much data should we use to be optimal? And what this paper does is it does the same thing. It examines this, but it adds in the new dimension of how much data are we training on. And what they find is that the previous scaling laws provided by OpenAI were actually a little bit off. And if we actually scroll down a bit, what we'll see is a graph that shows us their new model, Chinchilla. And this is a model that is 70 billion parameters compared to some other models they show, like Gopher and GPT-3, that have well over 100 billion parameters. Even though Chinchilla is smaller, it actually performs better than these other models with the same amount of compute and less parameters. And the main reason that it looks like these scaling laws were off previously is because they weren't taking into account the amount of data you should be training with. It turns out as these models get really big, you need even more training data. We'll move on to the next paper now, but if you are interested to see more on this, I do have a video on my channel. I'll link in the description about this. Next up, we have beyond neural scaling laws, beating power law scaling via data pruning. And this is, as you can see, another paper paper about scaling, and it talks about as how we scale up our models, we can actually do better than the scaling laws we just talked about in the previous paper by essentially pruning our data and only taking certain data. Now, while current models do scale very well, the actual rate at which they scale is maybe not super efficient. Having a power law means that for a reduction from like 3 to 2% error on something, it may take roughly like 10 times more data, compute, or energy, as they point out in this paper, which is not great. And what they show here is that by instead of using all the data, if they take certain types of data, they can reduce the power law scale to more of an exponential scale, which I mean is still not perfect, but it's still quite a bit better than having power law scaling. One of the interesting things they find is that the optimal strategy for how you prune your data actually depends on your initial amount of data. For example, when you have lots of data, you only want to keep the hard examples, but when you have small amounts of data, it tends to be easier to only keep the easy examples, which is pretty cool. And they have some neat visualizations showing these actual numbers. Now, at first they calculate this in theory, and then they actually try it out in practice to see how well the results hold up, and they give a pretty thorough comparison. This method also only uses self-supervised learning, so while there have been previous methods for doing data pruning, this one doesn't require labels, which is very nice. And then we have on-demand sampling, learning optimally from multiple distributions. This paper deals, as you can see, with learning multiple distributions. Now they give a few examples where you might want to do this sort of thing and what they mean by multiple distributions. For example, maybe you are in a setting where you really care about fairness, and to make things fair, you have to train on distributions from different populations, which, have many different traits. Or maybe you want your application to be very robust, which means that you're going to have to capture certain uncertainties that appear in the underlying task, and those could be modeled as different distributions. Another setting where you might be learning from multiple distributions is when you have multiple agents, and this also extends to federated learning, where you have these different agents, but each agent might have its own task. Hence, those are going to be different distributions you're trying to learn from. So you can see there's lots of different scenarios where addressing this sort of problem could be useful. You could imagine you could make this problem very simple by just say you have in distributions, you take so many examples from each of them and you just train on them as you would normally an entire data set. But as it turns out, you can do this much more efficiently because there are other things to consider when you're learning from multiple distributions. For one, some distributions might be easier to learn than others, so they might need less samples to learn. The other thing is that some distributions may be very similar. For example, if you have different populations in nearby areas might be more similar, which means you don't need as much training data from both because there's lots of overlapping correlations that could be learned. So how they address this problem in this paper is they derive sample complexity bounds that are better than what had previously been derived. So that's the sort of the theory part of it. And then they give a corresponding algorithm that can do this and sample on demand from those distributions, which, as they say in the paper, means they're sampling from these distributions during the algorithm whenever they need them and from whichever distribution. To wrap this up, we have two datasets / benchmarks to go over that also got one of these outstanding rewards. The first one is Lion 5B, which is 5 billion, an open large-scale dataset for training next-generation image text models. Now, unless you've been living under a rock, I'm sure you've seen all the diffusion models, all the image to text stuff. It's awesome. Previously, that was sort of all being done by private companies that had their own data sets for doing this, and they were scraping them from the web, which meant it was pretty inaccessible if you maybe want to fine-tune one of these on some new data. There was only so much data out there. But Lion 5B, this is over 5 million samples of these, and these samples they put in the data set are actually filtered by a clip model, which means that they're, filtering out some of the bad ones. And I'm on their website right now, and if I scroll down, you can see they have the download links just right here. So, I always love stuff that's open source, that's giving people the power to do these experiments on their own instead of restricting them. So it's awesome. I'm pretty sure this is what Stable Diffusion was trained on. This isn't like a super new data set. It's kind of new, but it's not like new. But anyway, incredible asset to the research community. Let's get into the next one, which is MineDOJO. Now, I actually considered covering this on my channel, but I didn't because this is about Minecraft and I had just published another video about Minecraft, but I really love this. And I think this has gone like criminally underlooked or underrated. We've had some Minecraft stuff in the past, but this really has everything. This has data of various formats from YouTube. They take YouTube videos, they take scrapes from Wikipedia, and they also have scraped lots of Reddit asking questions about Minecraft, answering questions about Minecraft. So there is a huge multimodal data set here about everything Minecraft, and this data set is huge. If you want to do Minecraft stuff, this data set is awesome. Not only do they have the data, but they also have predefined tasks like you can see right here: craft a glass bridge, build an oak house, make ice igloo. And not only do they have the tasks, they also have baseline models for these and implementations that work quite well. I mean, you know, they're a bit rough, but they're better than most things out there. And they're rough because this is a really hard task. And you know what's the best thing for solving a really hard task? It's having a great set of data and environments to experiment with. And, you know, here we have this. So really kudos to everyone working on open data sets and benchmarks. It is important work. This is my first time doing an overview of an entire conference. So let me know what you thought of this. If you think I should change it up, do it again, not do it again. Anyway, if you have liked this, consider subscribing or maybe following me on Twitter for some hot takes. Thank you so much for watching, and I hope to catch you next time.